Okay, hello and welcome back. Today what we'll do is wrap up our discussion of Fourier transforms of signals. So the topic today is kind of going to be loose ends. Okay. All right. So the lecture today will probably be a little shorter than the last few have been. And then we'll talk about Fourier transforms of distributions, which will be a larger discussion starting next time. All right, so for today, the first thing we'll talk about in our loose end discussion is Fourier transform and convolution. Okay, so I'm just kind of gonna, give the answers here. Generally speaking, the things that I'm going to write down today, proofs tend to just be applications of Fubini's theorem and direct computations. And if you are of the personality type that just freely swaps the order of integration without thinking about it, then you can forego Fubini's theorem. But I recommend understanding the role of Fubini's theorem and all of these things. Okay, all right, so we have four transforms. And so we're going to have results for each of these four kinds of transforms, and they will differ slightly depending on the transform. Okay, all right. So and so for the for all these transforms, there's kind of two things to consider. Okay, so the first is what is the CDFT of a convolution. Okay, and so what we'll see is that under appropriate hypotheses, the CDFT of a convolution is the product of the CDFTs. And so then you can also think about what is the CDFT of a product. Okay. All right, and so products in convolution in Fourier transforms turn out to be intertwined in interesting ways. And the moral of the story, more or less, is the CDFT of a convolution is a product, and the CDFT of a product is a convolution. Okay, so let's sort of state things precisely. Okay, so if things are generally nice for L1 things, sometimes for L2 things you have to be more careful, and I'm not going to talk about L2 things. You can look at the detailed statements in the course notes, and they resemble this, but sometimes you need additional hypotheses. Okay, so let's first start with F and G in L1 per. Okay, so this is the natural domain of the CDFT. All right. Now, the important thing to note is that if F and G are in L1 per, then one of the things we saw when we talked about convolution is the convolution likes L1, and so it takes things in L1 and returns things in L1. And this is a statement which is true for kind of all flavors of L1. In this case, it's L1 per. Okay, and so certainly this thing then is definable in a normal way. Okay, and it turns out, as I sort of suggested, that it's the CDF, the product of the CDFTs. Okay, all right. So that's how things work for CDFTs of convolutions. Okay, and so again, what you want to do then, because there seems to be a connection here with convolutions and products, is you maybe want to ask what's the CDFT of a product. Okay, so now it's not true that L1 in this case or in any other case is, well, except for the finite dimensional discrete case, that L1, sorry, discrete periodic case, that L1 is preserved by product. Okay, so you need, so in other words, if you just take F and G in L1 per, which you need to do to define their CDFTs in the normal way, but it's not going to be true that the product of F and G is going to be an L1 per. Okay, so you need some additional assumptions here in order to make a statement. Okay, and if CDFT of F and CDFT of G are in little L1, then, okay, we're going to write down the CDFT of FG, okay, and that's going to be the convolution of the CDFTs. Okay. All right, so this statement is quite restrictive, actually, because the hypotheses actually say much stronger things about F and G than merely that they be in L1 per, because we've seen when we talked about uniform convergence of Fourier series, this condition, the transform, the CDFT, be in little L1, has strong implications for the signals themselves, and namely that the signals themselves are almost everywhere equal to a continuous signal. Okay, and so in other words, what this really means is that morally, F and G are really continuous, right? So there's, and if they're not continuous, there's a unique representative in their L1 equivalence class. All right. And so therefore FG will also be continuous. All right, so so in this case, certainly the existence of the CDFT is okay, right? And that's because it's not, we're not really talking about L1 here, we're really talking about C0. All right, okay, good. All right, so that's the CDFT. Let's look at the CCFT. Okay. All right, so a similar kind of thing holds. So again, we're going to consider two questions, namely the CDFT of a convolution and the CDFT of a product. Okay, and we're going to again see that product and convolution kind of get interchanged by transform. Okay, and so we'll just jump right into the precise statements. Okay, so one, if F and G are in L1, okay, so again, convolution likes L1, and so if F and G are in L1, then their convolution is also in L1, and so we can take its CCFT. Okay, and the CCFT of a convolution is the product. CC right? All right, good. Now, what about then the CCFT of a product? And so again, we run into this exactly the same problem as we had with the CDFT, and that is that if things are in L1, their product is not necessarily going to be in L1, so you need some additional conditions, and the additional conditions are going to exactly be those that we made for the CDFT. Okay, so if F and G are in L1, and if they're CCFTs, okay, so then the CCFT of the product is the convolution of the CCFTs. Okay. And so I should make it clear here that this convolution here is a continuous time periodic convolution right in here, and this convolution here is a discrete time aperiodic convolution. Okay, so that this convolution is defined with a sum, and this one's defined with an integral, and here they're all defined with integrals. Okay. All right. Now, what about DCFT? Okay, and so again, we can just jump directly into the correct statements. Okay, and it's the idea here now becomes familiar. Okay, so again, if F and G are in little L1, then their convolution is also going to be in little L1. Okay, that's what we saw when we talked about convolution. And so they are therefore candidates to have the DCFT defined. Okay. And the DCFT of a convolution is the product of the DCFT. All right. Okay, and same thing for product. Okay. Okay, but now for in the discrete time case, all right, so now if F and G are in L1 of, okay, then it turns out that you get a nice convenience that happens here. Because what happens is that this is in L2, okay? And because it's in L2, you can then use, right, so this is now a property of infinite discrete time signal spaces, right? That the little L spaces are contained in, L1 spaces are contained in the little L2 spaces, okay? So it's the opposite of what happens with bounded time domain continuous time signals, where big L2 is contained in big L1, all right? All right, so this is now a convenience that comes from discrete time. Because you have this, you can then use the Cauchy-Schwarz inequality to say some things about the convolution of something in L1. Sorry, the product now is going to be actually in L1. Okay, so So I don't actually need any additional hypotheses in this case, is the point. Okay, so it's FDC of FG of nu DC of F of nu C of G of nu. Okay, so a little bit nicer in that case because of the discrete frequency domain. Okay, and then finally for the DDFT, of course, you expect everything to sort of work out with no special requirements, and that's of course the case. So if F and G are in, okay, so remember that we're talking about periodic signals with period t, so n delta, okay. Right, on the sampled time domain, z delta. Right, so then we're taking the periodic discrete convolution, the periodic discrete Fourier transform of the convolution, right? So it's going to be f d of f star g of, so remember now these are going to be frequency signals with a sampling interval of 1 over n delta. That's what we saw come out last time. Right, and so the DDFT of a product is, or sorry, of a convolution is the product of the DDFTs. Okay. And then, of course, the opposite one also holds with no restrictions because, of course, everything's finite dimensional. And so if F and G are in here, then, of course, their product is 2. Okay, then F D of F G. It's the convolution. So it's oh, sorry, I made a typo up here. Okay, and I hope I didn't. Yeah, I think it was the only place I made that typo. All right, so it's F D of F, convolution of F D of G at M delta. Okay, so for the DDFT, everything works without restriction. Okay, all right, so note there are also variants of some of these convolution product results. For the L2 or little L2 Fourier transforms. Okay, but I'm not going to state them. You know, they don't there's not analogs of everything. Some things require additional hypotheses to hold in L2, so you know you need to be careful with how you do that. You can't just replace 1 with 2 and everything works. That's not the results. Okay. Okay. And so, you know, you'll maybe remember in a differential equations course, so when you maybe used Laplace transforms to solve differential equations, that you saw that the Laplace transform interacts nicely with convolution in exactly this way, that the Laplace transform of the convolution is the product of the Laplace transforms, okay? And there's hypotheses there, but we will talk about Laplace transforms later on. But maybe you've seen these kinds of interconnections between convolutions and products and transforms, right? Okay, good. Now, what I want to do is I want to talk about sampling and periodization. So I've mentioned this many times, and I'll talk a little bit about it here. Not as much as I think I would like to. I wish that I had sorted this out and written down everything as completely as as is possible, because I think it's a very beautiful story, but I didn't do that, and so I'll tell you what I know. Okay, so first of all, there's two operations, sampling and periodization, so let's talk about them. Okay, so given a continuous time signal f. Okay, so we're talking about things Fourier here. So we're just going to take all signals to be continuous time signals to be defined on all of R, and we're going to think about them as being complex valued. Okay, so given one of these and some delta, a positive real number, we can define the sampled version of f to be, let's call it maybe just a f, or f hat, too often means transform, so let me just call it let me just call it FD for discrete time version. Okay, so this is going to go from Z delta into C, and it's going to have the obvious definition. It's just going to be F sampled at, or evaluated at the integer multiples of delta. Okay, so one thing to note immediately is that this is a pretty senseless process unless f is continuous. Okay, not continuous time, but continuous. Continuous as a function of t. Okay, and the reason is that if it's discontinuous, then really you're talking about functions that are equivalent in the sense of being equal except on a set of measures 0. So discontinuous signals really, the class of signals to talk about, they're really measurable signals, and so then it's equivalence classes that you're talking about, because and if you're talking about things that are only measurable, then a thing like this is really kind of meaningless, right? So if you choose a specific time and you just measure the value of f at that time, unless f is continuous, in which case the equivalence class of f contains a unique continuous signal, this really doesn't have a lot of meaning, all right? So sampling signals is really only a valuable thing if your signals are continuous, right? Okay, so that's what sampling is, okay? What about periodization? Okay, so periodization takes a, and so sorry, just to, this process here is valid if f is periodic or aperiodic. I've made no assumptions on what f looks like here. Okay, so this discretization can happen for periodic or aperiodic signals. Okay, and if you're periodic, then you're probably going to choose delta to be the period divided by some number, which we previously denoted by capital N. Okay, just so that n delta is equal to the period. Okay. All right, so now what we're going to do is we're going to take, again, a continuous time signal. And so this definition of sampling always makes sense. Like I said, it really only makes sense in the case when f is continuous as a function of t, right? But the definition itself has no ambiguities. Okay. This definition doesn't always make sense. Okay, but I'll just write down kind of the vague definition. So given a continuous time signal f from R to C, and given a positive time t, okay, we can define the t periodization of f. And we talked about this before when we talked about approximate identities, and we talked about Dirichlet kernels and Faget kernels, and I wrote down some formulas there about the periodization of these. Okay, now we're going to talk about them in the context of Fourier transforms. Okay, and so it's going to be per t of f. Okay, and so I guess really I should have done something like SMPL delta of f is probably how I should define that if I were to do this for real. Okay, and so the idea is that you define it by some j in set of integers f of, sorry, this is going to be evaluated at t plus jt. Okay. All right, so of course, this sum will generally not converge, right? And so you need to put some properties on f in order to guarantee that that thing converges, okay? So we'll say f is t periodizable if the sum above converges for almost every t. Okay, so the idea here is that you have some f, which maybe looks like something like this. Okay, and then what you do is you're just, so t and minus t and minus 2t and 2t. You're taking and shifting okay, f by integer multiples of the period t, and then you're adding all that stuff up together. Okay, and the idea, and so if this sum makes sense, then certainly f is t periodic. Okay, okay. All right. Okay, so note that per T of F is T periodic if F is T periodizable. Okay, and that's true because just because per T of F of T plus capital T is okay, and so you're just putting a j plus 1 there and summing over j plus 1 over all integers j is the same thing as summing over j for all integers j. Okay, so this is sum j equal j in z of f of t plus jt. The sums are the same. Okay. All right, so now you need some conditions on F to ensure that it's periodizable. So if F is in L1, then F is T periodizable for every T. And moreover, its T periodization is in L1 per. All right, and that's just a direct calculation. All right. Okay, so we've talked previously about examples of periodization. So I gave you the formulae for the periodization of the Fedget and Dirichlet kernels. Very beautiful formulae. I'm so happy I worked those out. Okay. Now what you would like to do, and what we've observed in various examples, is we've observed that there's some sort of connection between CCFT, CDFT, and sampling and periodization. Okay, and there's a general thing which captures that, and it's called the Poisson summation formula. Okay, and here's how it reads. If F is in L1, then, okay, so we know from the previous proposition that it's T periodization is in L1 per, okay? And so we can calculate, therefore, its CDFT all right, and this is exactly the sampled CCFT for F. Right, and again, this is just a direct computation, right? All right, and so you see this formula being manifested in some of the examples that we looked at, okay? And there's other flavors of this because we saw this sort of show up in multiple contexts, right? Discrete time, periodic, continuous time, aperiodic. And so there's other versions of this that one can write down, but I haven't had time to sort of work through that all super carefully, okay? All right. Okay, so that's going to conclude what I wanted to talk about today. So as I say, next time what we will do is we'll start talking about Fourier transforms of distributions. And so this will, and so I'm going to do that kind of quickly, not getting into a lot of depth, but I want to sort of discuss all the main players there and how they all fit together. So we'll start that next time.